Hello, I'm Ganon, a PhD student at Sangkyungan University. I'm excited to share that our paper DIA, the adversarial exposure of deterministic inversion in diffusion models, has been published at ICCV 2025. I believe this video will help you understand our work, so let me begin the introduction. Recently, we may be aware that text-to-image generative models like Stable Diffusion are causing severe social problems. As you can see in the image on the right, models trained on publicly shared images can achieve style mimicry and model personalization. In response, a technology called adversarial noise has been reframed as image immunization, emerging as a method to suppress deepfake generation. Initially, ADVDM and PhotoGuard became representative methods for disrupting generation in diffusion models. And subsequently, image immunization models like Glaze and Anti-Dream Booth, which suppress style mimicry and personalization models, were proposed. As shown in the image on the right, both Glaze and Anti-Dream Booth are models that disrupt scenarios where images are learned by models. However, there are still no immunization methods that can suppress image editing. As you can see from the title, we propose an immunization method against DDIM-based image editing techniques. Our method DIA directly bypasses the DDIM inversion trajectory, disrupting the acquisition of unique latent codes or reconstruction. Now this approach faces an out-of-memory problem, which we solved by decomposing backpropagation on a per time step basis and using a method to compute the Jacobian product. In the following slides, I'll demonstrate that this is both theoretically and experimentally sound. The overall immunization and suppression scenario is shown below. When an original image is immunized through adversarial noise, this image can no longer be edited normally. Before diving into our methodology, let me remind you about DDIM sampling and inversion. First, looking at the equation in the upper left, when sigma in this equation is 0, we call it DDIM sampling. And as shown below, through the assumption of linearization, we can also express the process from image to noise in a deterministic inverse manner. The important point to note is that each step consists of the strength from the previous step and predicted noise. And then we can recursively rearrange the previous equation to express latent code x large T in terms of x0. Here, the right-hand term of this equation can be viewed as the model trajectory, and we represented the process trajectory by adding the decreased x0. The time-stepwise strength of x0 plays a crucial role in pivoting the model trajectory. The method that disrupts this process trajectory is DIAPT, which prevents the acquisition of the latent code, the result of the inversion process. And next, DIA-R adds a reconstruction process to the same approach as DIAPT to disrupt the reconstruction process. As shown in the image on the right, you can think of it as the reconstructed image moving away from the original image. This method may seem quite straightforward, but there is a problem with backpropagation. To construct the DDIM trajectory, time-stepwise inference is absolutely necessary. However, time-stepwise parameter gradient accumulation causes severe memory consumption. Here, we decomposed the propagation to compute time-stepwise vector Jacobian products, which uses a fixed amount of memory regardless of the trajectory length. The cloned latent and partial backpropagation in this figure are used for this purpose. The equation below shows the time-stepwise vector Jacobian product. The qualitative results are as follows. Other immunization methods are designed to attack only the encoder or a single step of diffusion, so they fail to suppress or show weak performance. However, you can see that DIA demonstrates strong suppression performance. These results are also supported by quantitative results. We conducted a total of 6,300 evaluations using 700 image prompt pairs from PyBench and 9 inversion edit scenarios. The left table shows clip similarity scores, which indicate how relevant the prompt and image are. In this table, lower performance in natural edit is better, and you can see that DIA outperforms the baseline. Also, editing tasks should preserve the background except for the desired region. In the right table, we demonstrated disruptive performance as well. Finally, this slide addresses robustness under various settings and stealthiness. In the upper left figure, we show better performance than the baseline across various epsilon budgets and even with long sampling steps. And it works robustly even under various purification methods. Lastly, DIA achieves imperceptible immunization even though it doesn't have a term for stealthiness in the loss function. Thank you for your interest in our paper.